Suppose you want a generative model that can not only dream up new images, but also tell you the exact probability of any data point you hand it. GANs simply can't do that. VAEs only ever give you an approximation. It sounds almost too good, one model that both generates and scores likelihood exactly. Yet a normalizing flow delivers precisely this. And the secret is a beautifully simple idea borrowed from calculus, the humble change of variables rule. It builds a perfectly reversible bridge between plain noise and rich data and lets you cross it in either direction. Let's walk across it. At its core, a flow is a chain of reversible steps. We start with something simple and morph it one invertible layer at a time into something complex. Follow the pipeline in order. Begin at the left with a simple base distribution, usually a plain Gaussian. This is noise we understand completely and can sample from trivially. Every rich, complicated image the flow will ever produce starts life as one of these boring random vectors. Now, push that noise through a chain of invertible transformations. Each layer bends and reshapes the distribution a little, and because every step is one-to-one, nothing is ever lost. Stack enough of them, and plain noise gradually becomes the intricate shape of real data. That is the whole trick, many small reversible moves adding up to one expressive mapping. Out the far end emerges complex data, a realistic sample. But here's the quiet genius. At every step, the model also tracks the Jacobian determinant, the exact factor by which that layer stretched or squeezed space. And that bookkeeping is what makes probabilities computable. And because each layer is invertible, you can run the entire chain backward. Feed in a real data point, push it back toward the Gaussian, and the change of variables formula hands you the exact probability density. No approximation, no bound, just the true number. So why go to all this trouble for reversibility? Here's what it buys you, set against the alternatives. Most popular generative models can't tell you how likely a data point actually is. A GAN has no probability output at all. It only produces samples. A VAE gets closer, but it optimizes a lower bound and hands you an approximation, never the exact number. For many jobs, an estimate simply isn't good enough. A normalizing flow, by contrast, is built entirely from invertible steps, and that single design choice unlocks exact likelihoods. Because the mapping is reversible with a tractable Jacobian, the change of variables formula gives you the precise density of any point. You get honest, exact probabilities rather than a clever guess, and you can train directly on them. Strip it all away, and 3 ideas defined a normalizing flow. It's a stack of invertible transformations. A perfectly reversible bridge maps a simple base distribution to complex data, so you could travel either direction, noise to data to generate, or data back to noise to analyze. It gives exact likelihoods through the change of variables formula. Because the Jacobian determinant of every step is tractable, the model computes the true probability density of any point, something GANs and VAEs simply cannot offer. You get the real number every single time, and it trains by directly maximizing that exact likelihood, with no adversarial game to balance. That makes training stable and principled, which is why flows shine at density estimation, anomaly detection, and variational inference. The price is a constrained architecture and a heavier memory footprint. All right, let's lock in what matters. A normalizing flow transforms simple noise into complex data through a sequence of invertible, one-to-one steps you can run in either direction. Because every step is reversible with a tractable Jacobian, the change of variables formula yields exact probability densities, with no approximation at all. That exact likelihood lets you train by directly maximizing it, stably and without adversarial games, which is ideal for density estimation and anomaly detection. The trade-off is a constrained, reversible architecture that costs some expressiveness and memory. Yet those exact probabilities are uniquely valuable. If you like generative AI mapped out this clearly, a whole library of explainers is waiting for you at standarity.com. Come flow with us.